Continuing on with the idea, our main idea is how are we going to solve exponential equations? How are we going to find that exponent we raise any base to find our antilog? So we're going to skip down to 4a, b, and c, and I'm going to show you and think through how I would like you to process through this information. We've been working for years on knowing how to do the inverse of an operation when we see it. So in 4a, what we really want to do is we want to solve this equation for y, but y is in the exponent. Now, what have we learned that will undo exponents? And the inverse of an exponent is a logarithm. So what I'm going to use is a logarithm to help undo a log or an exponent of base 8. So what I could do is there are different strategies here. I'm going to apply the first one here. I could undo a log or an exponential of base 8 by using the log of base 8 of 8 to the y equals the log of base 8 of 0.165, and this is relating back to their one-to-one property that we had before. If these two sides, if this expression is equal, then the log base 8 of each of them has to be equal as well. The reason the choice of log base 8 is good is because log base 8 of 8 will undo each other. They are inverses, so they cancel out, so y equals, then we got a log of base 8 of 0.165. Now that becomes problematic because it's not one of our convenient bases, and we don't really know what would I raise 8 to get 0.165. It's not something that we're going to be able to do mentally. So what we learned in the prior lesson 3.3 is if we have an inconvenient base, what we can do is we can simply use our change of base formula. We could use a common log of 0.165 divided by the common log of 8. And that will help get us our solution, and we were asked to round it to the nearest hundredth, so we simply type in our calculator this expression and round it to the hundredths place. So we take the common log of 0.165 and we divide it by the common log of 8 equals a negative 0.87. So this is approximately a negative 0.87. Now this is just one of many different ways of doing this. Let me start off by showing you another one here. We have 8 to the y equals 0.165. Now last time I chose to do a log base 8. That is just kind of the intuitive way of doing this using their one-to-one idea and using your inverse of logarithms. But you can also approach this by just using either a common log or a natural log. To undo an exponent, what we want to do is we want to perform a log. So we can do a log, a common log of 8 to the y equals the common log of 0.165. Now you notice I didn't use a base 8 logarithm. So what I'm going to do now is the statement is I just did common logarithm on both sides. As long as we take the logarithm on each side, we create an equivalent equation. It's the same thing you've done, it's just that we're using a new operation, logarithms. This is the log property of equality. I just took the log of base 10 of each side. Then we can use our power rules. And when I say the power rule, this is the power rule of logarithms. The log of a power is the power times the log. So it's y times the log, common log of 8 equals the common log of 0.165. If I want to get y by itself, I do the inverse of multiplying by the log of 8, and y equals the log of 0.165 divided by the log of 8, which is identical to what we have over here. It's just that if I start off by using the log of base 10, I don't have to use the change of base formula. And finally, just to show you that it doesn't matter what you use for a log base, I can get you the exact same result by using a natural logarithm. So any logarithm will undo an exponent. They may not be the true inverses, but they will undo that logarithm or that exponent. So I'm going to show you that if I use the natural log of 8 to the y, and as long as I apply the natural logarithm to both sides, the log property of equality, I can get an equivalent expression, even if it's a natural log. Then I'm going to use this power rule of logarithms. It's y times the natural log of 8 equals the natural log of 0.165. And I can get rid of multiplying by the natural log of 8 by dividing by the natural log of 8. So the natural log of 0.165 divided by the natural log of 8. And I wanted to show you this so that you didn't have to worry about which log base that you use. And that means I have the choice of using the common log, natural log, or base 8 log, and I can get the same result. So the natural log of 0.165, if we divide it by the natural log of 8, we get the exact same answer that we had in our first go around. So you've got lots of choices here. You can divide, or you can multiply both sides, or take the log of both sides of log base 8. That'll be fine. You can do the log base 10. That'll be fine. And you can also do a log of base e or natural log. Hopefully you're seeing some carryover. Once we got to this stage here, we had a choice. We could do a log base 10, change a base formula, or at this stage we could have done a log base e, which would have been natural log of 0.165 divided by the natural log of 8, which is what we have over here. So we have some flexibility, folks, and flexibility sometimes creates a little anxiety, but it should also open some pathways to help us resolve some of these issues that we're going to have solving exponential equations. So let's go to 4b. On these equations, the first thing, I didn't have to do it in the first problem, but the first thing I want to do is I want to isolate the exponential expression. Okay, so I want to isolate this 1.43 to the a. I want to isolate it. And if you just carry out your PEMDAS backwards, that's going to take care of itself anyway. We want to undo anything that's attached to our variable that's added or subtracted first. So that means I got 1.43 raised to the a. I want to subtract 3.1 from the other side. So it's 8.48 minus 3.1. And I'm not very good at doing that mentally. So 8.48 minus 3.1 gives us 5.38. So 5.38. Now I've got the exponential expression isolated. Now I want to undo that. So 2. I want to undo the exponent. To undo the exponent, we're going to elicit the inverse. So I've got to be thinking of what is the inverse of an exponential, and that is a logarithm. Now, as I said, we have a lot of different things that we can use. We could use a log of base 1.43. Not my first choice. I don't want to have to use a log of base 1.43, but that's using that one-to-one concept. For me, the two choices are pretty set. It's either natural log or common log. As long as you use either one of those, it'll undo our exponent, because we'll be able to use our log rule. So I'm just going to use a natural log. It's a little bit shorter. That's how I guess made that determination. The natural log of 1.43 raised to the a. Whatever I do to one side, I took the natural log of the left, I must do the natural log on the right, so the natural log of 5.38. So we took the logarithm of both sides, so log property of equality. Followed by the log property of equality, you're almost always going to follow that with your power property of logarithm. So the log of the power is the power times the log. So the natural log of 1.43 equals the natural log of 5.38. Now I want to get a by itself. To get a by itself, I simply divide by the natural log of 1.43. So natural log of 5.38 divided by the natural log of 1.43. That's our calculation. We round it to the nearest hundredth and we're set. So clearing that off, let's do the natural log of 5.38. Close the parenthesis, divided by the natural log of 1.43, parenthesis, enter. Our answer should be 4.70. So A is approximately 4.07. Okay, just double check, and that's what it was. Nope. That's why I double checked. 4.70 to the nearest hundredth. Okay? I don't want to keep stretching this out any farther than it has to, but I want to come back up here, and at this point in this problem, we still want to isolate that exponential. So now I got 1.43 to the a equals 5.38. Remember, I had a choice. I used natural log the first time. I can use the common log. That's in my calculator. So 1.43 raised to the a equals the common log of 5.38. Bring down your power rule. A times the log of 1.43 equals the log, common log of 5.38. To get a by itself, we would take the common log of 5.38 and divide it by the common log of 1.43. We should get the exact same result. That's the last time I'll kind of cross-reference that for you. So I want to keep pointing out it doesn't matter what log base you use. It's 5.38, and of course eventually we're going to want to stick with our log of base 10 and log of base e, because those are the only two that we have on here. Otherwise you're going to end up having to do a change of base formula. So log of 1.43, parenthesis, we should get the exact same value, and it is. Okay, and there's one more example here that they want us to go through. Using our order of operations backwards, addition, subtraction. We want to get rid of any addition, subtraction, but the problem is this addition is up in the exponent, and we can't get rid of that exponent. We can't get rid of the addition until we undo the exponent. So we're going to really have to follow those order of operations and carry them out backwards very carefully. So the first thing we want to do is get rid of our logarithm of base e. Now a great choice would be the natural logarithm, because the natural logarithm of e to the 2 plus 5w equals, if I make the natural log on the left, I take the natural log on the right. So log property of equality. But the great thing about this is an inverse. This is a natural log of an exponential base e. They reduce each other, so we got 2 plus 5w equals the natural log of 12. Then what we can do is we can carry out solving this linear equation. So 5 times w would have to equal the natural log of 12 minus 2, and then w would have to equal the result of the natural log of 12 minus 2 all over 5. So we'll run that calculation through. We'll do the natural log of 12, and we'll subtract 2 from that. And since I didn't get parentheses around it, I'm going to hit enter. We got to take that answer and divide it by 5 and round it to the nearest hundredth. If we round that, that 6 is going to create a 1. So 6 creates a 9, become a 10, carry the 1. So really get w is equal to approximately 0.10. Okay, so solving exponential equations. Really the base idea here is to get rid of your exponent by using logarithms. We're really adding a step to your solving equations with this PEMDAS backwards. We've always been able to undo addition, subtraction, multiplication, division. Now we're undoing unknown exponents.